Welcome to Tomorrow Unveiled.
It feels like the last week, maybe 10 days of September 2025, weren't just another step for robotics. It feels more like a fundamental shift, a real inflection point.
Yeah, I agree. We've been hearing about humanoid potential for, gosh, seems like forever, right? Robots that look like us, walk like us.
Interact like us, but mostly theoretical or very limited demos.
Exactly. And the research team that put all this together for Tomorrow Unveiled, they were really clear this past week. It signals a move away from just, lab prototypes.
Or those flashy tech demos we see sometimes.
Right, towards systems that are actually deployable. Humanoids that can reason, that are general purpose. It's not quite the sci-fi rise of the machines yet.
No, not Skynet.
Not yet, anyway. But it is about real, tangible breakthroughs, integrating some incredibly sophisticated AI with, frankly, equally advanced mechanics.
And you saw this convergence everywhere. Big announcements at major conferences like QDRL and IE Humanoids.
And for the big tech players, too. Google, Nvidia, Meta, they all had something major to say.
So our goal here on Tomorrow Unveiled is really to cut through the noise. Give you, our listener, the consensus view of what just happened. The shortcut, if you will.
And that big shift you mentioned earlier, that's the core of it. We're moving past robots built for just one single thing.
Like tightening the same bolt on an assembly line forever?
Yeah, exactly. We're talking about general-purpose agents now.
Yeah.
Robots that need to understand our messy, unpredictable world.
They need to perceive it, reason about it, maybe even deal with vague instructions like clean up this area.
And plan complex, multi-step tasks. And crucially, adapt on the fly when something changes. That's the hard part.
That cognitive piece combined with the physical ability, that's the quantum leap we saw hints of this week.
Okay, so let's start with that cognitive revolution then. Because giving these robots a proper brain, that seems like the headline news. And Google DeepMind was right at the center.
Absolutely. The big buzz was around agentic reasoning, specifically the release of Gemini Robotics 1.5.
Right, VLA. That's the term we keep hearing. Vision Language Action Model. We know about language models for text, vision models for images. What makes this VLA model different? Why now?
Well, think about how robots worked before. Largely, it was either hard-coded state machines, basically a long list of if this, then do that rules.
Pretty rigid.
Very rigid. Or something called behavioral cloning. You basically record a human doing a task, and the robot tries to mimic those exact motions.
Okay, so copycat robots.
Pretty much. And both methods fall apart the second the environment changes even slightly. If a cup isn't exactly where it expects, game over. They lack real generalized understanding.
So if you move the table an inch, the robot just keeps pouring coffee onto the floor where the table used to be.
Exactly. Gemini Robotics 1.5 aims to replace that brittleness. The real breakthrough is its ability to generate an internal reasoning process. It thinks in natural language about how to do the task before it actually moves.
Okay, think before acting. That sounds simple, but for a robot, that's huge.
Unitree. It's fundamental. It changes everything about safety, about the complexity of tasks you can even attempt.
So instead of just being programmed with, like, coordinate points, move arm to XYZ.
Right.
It gets a command, say, put the dirty dishes in the dishwasher. And then it internally generates a plan. Like step 1, find the dishes. Step 2, check if the dishwasher is open. Step 3.
Precisely. It might internally generate something like 1, identify dirty plates on the counter. 2, pick up plate carefully. 3, walk to dishwasher. 4, check dishwasher door status. 5, if closed, open door. 6, place plate inside, and so on.
And this internal monologue, we can actually see it, audit it.
That's the key. It makes the robot interpretable. We can understand why it's doing what it's doing, and it allows for much more complex multi-step tasks that require chaining abstract goals together, things that were, frankly, almost impossible before.
But real-world tasks are messy. What happens when step 4 fails? Like the dishwasher is unexpectedly full, or someone walks in front of the robot.
Good question. That's where the other part comes in. Gemini Robotics ER 1.5. The ER stands for Embodied Reasoning.
Okay, so 1.5 is the immediate action part, and ER 1.5 is the supervisor.
Sort of the high-level planner, yeah, the orchestrator. And this is where we really get into this concept of an agentic framework. It's a big leap.
Agentic framework. Break that down a bit. How's that different from just having a bunch of backup plans?
Well, classical planning usually relies only on the information the robot already has stored internally. An agentic framework treats the robot more like an intelligent agent that can actively seek out new information from the outside world.
External resources.
Exactly. ER 1.5 allows the robot to call external tools while it's working. The most obvious one, searching the internet. Using Google, for instance.
Wait, the robot can Google things mid-task.
Yes, and it constantly monitors its own progress using its cameras and sensors. If it hits a snag or realizes the situation has changed, it can dynamically replan the entire sequence.
So it's not just blindly following its internal script. It's checking the script against reality.
Yeah.
And if there's a mismatch, it thinks, I need more data, and goes looking for it.
You got it. It's self-correcting based on real-time information and external knowledge. And our research team noted this ER functionality performed extremely well, hitting state-of-the-art on like 15 different academic benchmarks for embodied reasoning. So it's robust, at least in simulation.
Okay, that example of the robot Googling, I need a concrete example. That sounds wild.
Okay, think about recycling sorting. A common task, right?
Sure.
A standard robot would be programmed. Plastic bottle in bin A, glass jar in bin B. But recycling rules are a nightmare. They change constantly, differ between cities. Maybe there's a new type of compostable plastic cup.
Right, the rules are always shifting.
So the old robot sees this weird cup, it freezes, doesn't match its rules. The Gemini 1.5 plus ER 1.5 robot sees the cup, identifies it as something unfamiliar, and its agentic reasoning kicks in. It decides, I need to know the local rule for this specific type of polymer.
And it actually searches online for recycling rules, my city, weird bioplastic cup.
Essentially, yes. It looks up the rule, understands the text it finds, and then performs the correct physical sorting action based on that real-time semantic understanding.
That's not just following instructions. That's applying common sense learned on the fly. That feels like a really profound shift.
It really is. It moves beyond simple logic into flexible, adaptable intelligence. And this combo also let robots do things requiring incredible fine motor control combined with that understanding.
Like what?
Well, the research mentioned things like folding complex origami patterns or carefully packing really delicate items into, say, a Ziploc bag, which is deformable and tricky.
It's not just the movement, it's reasoning about fragility and the precision needed.
Exactly. The high-level understanding guides the low-level motor control.
Okay, so DeepMind is providing this advanced reasoning brain. But a brain needs a place to learn, right? And how do you make sure what it learns in simulation actually works in the real, messy world?
Ah, yes. The sim-to-real problem.
Which brings us to the other huge piece of news this week. Nvidia's big ecosystem play. Standardizing the learning process itself.
Yeah, Nvidia made a classic, very ambitious platform move. They didn't just announce a new chip, though. They did that, too. They announced a whole standardized open source infrastructure.
Like trying to become the Windows or maybe the Android of humanoid robotics.
That's a good analogy, lowering the barrier to entry for everyone else building robots.
And our sources highlighted three main pillars for this platform. There's the hardware, right? Jetson Thor.
Yep. Jetson Thor, a powerful little supercomputer designed to run these complex AI models directly on the robot in real time with low latency, crucial for responsiveness.
But the really big levers seem to be the generalized brain and the virtual body.
That virtual body is the Newton physics engine. This is really interesting. It was co-developed with Google DeepMind, actually, and Disney Research, among others.
Disney. Why Disney?
Animation. They're masters of simulating realistic physics for virtual characters. Newton is GPU-accelerated, designed for super high-fidelity physics simulation, and its main goal, to finally solve that dreaded sim-to-real gap.
Okay, explain the sim-to-real gap. Why is it such a killer for robotics? If a robot learns to walk perfectly in a computer simulation, why does it fall flat on its face in the real world?
Because reality is infinitely complex, and older simulators, well, they cheated. They simplified everything. Objects were perfect rigid blocks, friction was uniform, sensors were noise-free.
Not like my slightly sticky kitchen floor or a wobbly sensor.
Exactly. So the walking skill learned in that perfect virtual sandbox just didn't transfer. The physics were fundamentally different. Newton tackles this by simulating all those messy, granular details much more accurately. Complex contact physics, deformable objects, realistic sensor noise.
So the goal is to make the simulation so realistic, the AI learning inside it basically can't tell the difference between the sim and reality.
That's the aspiration. The simulated friction, the joint behavior, the way light reflects. It all needs to mirror the real world closely enough that the learned skills, the policies, are inherently stable and transferable. GPU acceleration makes that level of detail computationally feasible.
Okay, so Newton provides the ultra-realistic virtual gym for training. Then what's the generalized brain part?
That's Isaac, GR00T, N1.6.
GR. GR00T and 1.6. Got it.
Yes. It's an open-weight reasoning system built on Nvidia's own VLM called Cosmos Reason. Think of GR00T as the API layer, the translator. It takes those vague human instructions we talked about, tidy this workspace, and uses common sense reasoning to break them down into the concrete, low-level physical actions the robot needs to perform.
Using the skills learned in the Newton simulation.
Precisely. It connects the high-level language understanding to the low-level physical control.
Now, the source has really stressed how quickly other major robotics companies are adopting this NVIDIA platform. We're talking Agility Robotics, Figure AI, even Boston Dynamics. Why jump on a competitor's platform? Isn't there a risk of being locked in?
It's a very pragmatic decision, I think. Building capable humanoid hardware is already incredibly difficult. Building the entire foundational AI stack, perception, planning, control, simulation from scratch is monumentally harder and maybe even redundant if someone else is providing a good open standard.
So they're offloading the foundational AI development to NVIDIA and Google.
Essentially, yes. They're saying, okay, you guys handle the standardized brain and the physics engine. We'll focus our expertise on building better legs, better hands, better hardware, and the specific applications that run on top of your platform. It de-risks their core business.
That makes a ton of sense. It must slash development time. Instead of spending years just getting the basic software stack working.
You can potentially get to application development in months. You leverage the massive R&D investment NVIDIA is making in the platform. It creates this powerful flywheel effect. Standardization fuels adoption, which fuels more investment in the platform, which accelerates innovation for everyone.
Democratization through standardization.
Mm-hmm.
Okay, so we've got smarter brains, better ways to train them.
Mm-hmm.
But what about the bodies? A genius AI is useless if the robot is clumsy or falls over easily. We saw some big hardware news too, right?
Oh, yeah. On the physical mastery front, KAIST, the Korean Advanced Institute of Science and Technology, really stole the show this week. Their lower body humanoid platform didn't just nudge the limits, it seemed to blow past them.
And our research team flagged something interesting about how they built it. Technological independence.
That was a key point. The KAIST team built basically everything themselves. The platform stands about 165 centimeters, weighs 75 kilograms, but the motors, the gear reducers, the control boards, all custom designed and built in-house.
Why is that significant? Why not use off-the-shelf parts?
Control and optimization. By designing everything together, they could push the performance envelope without being constrained by the limitations of generic components. And the results were, frankly, stunning. They demonstrated the platform running at 3.25 meters per second.
3.25 meters per second. Help me visualize that. How fast is that for a walking robot?
That's about 7.3 miles per hour, so a pretty fast jog. Maybe even a medium run for a person. For a bipedal robot, that's seriously quick. It changes the game for tasks needing dynamic movement.
Wow. And it wasn't just raw speed, was it? The reports mentioned some complex maneuvers, stuff that showed real resilience.
Definitely. They showed incredible proprioception in the robot, knowing where its limbs are without just relying on cameras. It could maintain balance even when they effectively blinded it by disabling the vision feed.
That's impressive.
And it performed complex skates, things like a controlled sideways duck walk, even a smooth moonwalk, which requires amazing coordination. And maybe most importantly, it climbed 30-centimeter steps. That's about a foot high.
Climbing a step that high without falling requires really sophisticated dynamic balance control.
Absolutely. And here's the kicker, connecting back to the simulation discussion. These advanced locomotion skills. They were learned using reinforcement learning, developed by KAIST themselves, trained entirely in simulation.
And they transferred successfully to the physical robot.
Yes. Another strong data point showing that the sim-to-real gap is genuinely being bridged, at least for locomotion.
And we saw other signs of this hardware agility trend too, right? Unitree's G1 model.
Yeah, Unitree showed off an enhanced anti-gravity mode for their G1. It allowed for some pretty nimble gymnastic-like movements and, crucially, demonstrated really robust recovery from being pushed hard. It popped right back up.
So the era of robots that just topple over if you breathe on them seems to be drawing to a close.
The hardware is getting seriously capable, but this rapid progress actually highlights a really interesting philosophical divide that emerged this week about the best way to achieve truly general, adaptable intelligence.
The adaptability paradigm, top-down versus bottom-up.
Exactly. We've mostly talked about the top-down approach so far. That's the Gemini GR00T philosophy, right? Intelligence starts with high-level reasoning, language understanding, and that flows down to control the physical actions. That seems to be the current consensus, driven by the big players.
Okay, so what's the alternative, the bottom-up approach?
Well, this week, we heard about a fascinating counter-philosophy from a company called Skilled AI. They talk about creating an omni-bodied brain.
Omni-Bodied.
Their idea is that true intelligence has to be deeply grounded in understanding physical reality first. They kind of argue that these VLM-first systems risk becoming very good at talking about physics, but maybe haven't truly mastered the intuitive feel for movement and interaction.
Okay, interesting critique. So how does Skilled AI propose to build this physically grounded intelligence? What's their training method?
It's pretty wild. They're training a single massive foundation model. But here's the twist. It's not trained just on one type of robot body. It's trained in a simulated multiverse containing over 100,000 different robot morphologies.
100,000? What kind of robots are we talking about?
Everything. Bipedal humanoids, yes, but also quadrupeds like dogs, hexapods, robots with wheels, robots with weird numbers of limbs, robotic arms, a massive diversity of physical forms.
That sounds computationally insane.
Yeah.
And maybe inefficient. If you ultimately want to control, say, an Apollo humanoid, why train it on how to be a robot dog or a six-legged spider?
That's the core of their hypothesis. They believe that training an AI only on one specific body type leads to overfitting. The AI essentially memorizes the dynamics of that single body.
Okay, so it learns the tricks for that specific robot, but not the general principles.
Exactly. If you then change something minor, remove a finger, add weight, put it on slippery ground, the whole system might break because it never learned the underlying universal laws of physics and motion. It only learned the specifics of its own body.
So by forcing this single AI model to learn how to control 100,000 radically different bodies.
Bodies with different numbers of legs, different centers of gravity, different ways of moving.
It has to extract the true general principles of physics, balance, interaction, things that apply across any physical form.
That's the theory. It's forced to learn not just how to balance this humanoid, but what is balance fundamentally, independent of the body plan. And the proof of concept anecdote our research team found was striking.
What was it?
Apparently, the skilled AI system can adapt almost instantly if you change the robot's body mid-task. Like if a limb gets damaged or removed or its weight distribution changes dramatically, it adapts in seconds without needing retraining.
Because it already understands the general physics principles.
It just applies its generalized physical knowledge to the new, altered configuration.
Wow. Okay, that really does set up a major philosophical crossroads, doesn't it?
Yeah.
Is general intelligence primarily about high-level symbolic reasoning, the VLM path, or does it emerge from this deep intuitive mastery of physical interaction learned across diverse forms, the skilled path?
It's a huge question. Maybe the future lies in some kind of hybrid approach, marrying the VLM's ability to understand human intent and plan complex tasks with the kind of inherent physical robustness Skilled is aiming for.
A fascinating debate with massive implications. Okay, before we get into how these different philosophies are playing out in actual commercial deployments, let's pause for a moment.
Good idea.
That's right. If you're finding this insightful, maybe learning something new, please take just a second to like this video if you're on YouTube, subscribe to Tomorrow Unveiled, and maybe even hit that new hype button. It really helps us get this analysis out to more viewers. And definitely turn on notifications so you don't miss what's coming next.
And if you're listening on the go, maybe on Apple Podcasts or Spotify or another audio service, we would be incredibly grateful if you could leave Tomorrow Unveiled a rating and perhaps a quick review. It makes a huge difference in helping new listeners discover the show.
Welcome back to Tomorrow Unveiled. We've covered the AI brains getting smarter, the platforms making training easier, and the robot bodies getting much more agile. Now, let's look at how these advancements are actually hitting the real world, or at least starting to. And this really throws the contrast between hype and pragmatism into sharp relief.
Yeah, and we have to start with probably the most talked about deployment or demonstration, which the community quickly nicknamed the Pop-Timus question.
Right, Tesla's Optimus robot. There was that high-profile demo this week set in a Hollywood diner, showing the robot doing things like serving popcorn, clearing some tables.
Classic high visibility stuff, great for capturing public imagination, shaping investor narratives. But
There's always a but in robotics demos.
there often is. It immediately sparked that intense debate within the robotics community. How much of what we saw was truly autonomous versus how much was maybe heavily assisted by human teleoperation, someone driving the robot remotely.
And our research team stressed why this distinction is so critical. They called for an autonomy audit. Why does it matter if it's tele-up or autonomous, especially for these public demos?
Because they prove very different things. If you can successfully teleoperate a robot to do complex tasks, it proves you've built a really good mechanical platform. Good joints, good balance, responsive actuators, solid controls. That's a major achievement in itself.
But it doesn't prove the robot is smart.
Exactly. It says nothing about the robot's own intelligence, its ability to perceive, reason, and act on its own. The robot is only as capable as the hidden human operator. So the sources suggest that while Optimus is mechanically advancing, the strategy might be more focused on building public perception and investor confidence right now, rather than necessarily showcasing cutting-edge autonomous operation in unpredictable settings.
Public relations versus proven autonomy. Often different goals.
Very different goals.
Okay, so if Optimus represents the high-profile, potentially hype-driven path, what's the counterpoint?
That would be the Pragmatist's path, and the prime example this week was Apptronik with their Apollo robot. Their whole strategy seems focused on immediate commercial value and proving reliability in real industrial settings.
Apollo got some recognition, right? Awards and stuff.
Yeah, it won a Fast Company Design Award, which is nice validation. But the bigger story is their focus on actual pilot programs. They're deploying Apollo units with major partners, Mercedes-Benz for one, and Jabil, a huge global electronics manufacturer.
And these pilots aren't for show. They're doing real work.
That's the plan. Focused, valuable, maybe slightly less glamorous industrial tasks. Things like logistics within the factory, fetching parts, delivering assembly kits to the production line where they're needed.
What makes this pragmatic approach maybe safer or more scalable right now?
They're starting in controlled environments. A factory floor is complex, sure, but it's way more predictable than a diner or home. Lighting is consistent, the layout doesn't change much, tasks are repetitive.
Manageable risk.
Exactly. It's the classic land and expand strategy. Solve a relatively simple but valuable problem reliably first. Prove your ROI, build trust with your customers. Then, as the robot and the AI mature, you gradually expand its capabilities into more complex tasks and maybe less structured environments.
But is there a downside to playing it safe? Does focusing only on factories risk making Apollo too specialized? Does it delay developing the kind of generalized intelligence needed for, say, elder care or home assistance?
That's the potential trade-off, yeah. You get immediate value, but the robot might become really good at factory tasks and struggle when moved elsewhere. Apptronik seems to be betting heavily on platforms like Nvidia's GR0T to provide that underlying generalized intelligence, hoping it'll be ready when they need to expand Apollo's horizons.
So Tesla's trying to leapfrog to the hardest problem now, maybe using tele-up as a crutch, while Apptronik builds a solid foundation on simpler tasks first. Two very different bets on how to get to general-purpose robotics.
Precisely. A really interesting tension to watch.
Okay, then there's a third narrative this week, focused more on democratization. And Unitree seems to be the main driver there.
Yeah, the sighting of a Unitree G1, which, remember, costs around $16,000 just being operated out in public, reportedly on a sidewalk in Sarasota, Florida. That's a huge symbolic moment.
Because just a few years ago, a robot that could walk like that would cost millions.
Millions. And it would be confined to a handful of elite, heavily funded research labs. Seeing it out in the wild at that price point signifies a massive shift.
How does that price change the innovation landscape?
It fundamentally flips the script. The main challenge is rapidly shifting away from can we physically build the legs and make them walk? That part is becoming increasingly solved and, dare I say, commoditized.
So the focus moves entirely to the software.
Entirely. The question becomes, okay, now that we have affordable, capable hardware platforms, what truly smart, reliable, useful software can we run on them? This democratization of hardware could unleash a Cambrian explosion of software innovation from smaller teams, startups, universities, people who could never afford to build the hardware themselves before.
Very cool. Okay, but amidst all this humanoid excitement, we also need context, right? For some jobs, maybe legs aren't even the best solution.
That's the specialized alternative viewpoint. Our research team highlighted Kinisi Robotics and their KR1 robot. They actually call it a wheeled humanoid.
Wheeled humanoid. So arms and a torso, but on wheels instead of legs.
Pretty much. And the founder was quite explicit, arguing that for many tasks, especially on flat industrial floors, legs are just unnecessary. Maybe even slow, unstable, and risky compared to a solid wheeled base.
It's a design choice, prioritizing immediate utility and efficiency over mimicking the human form factor.
Absolutely. The KR-1 is built for warehouse logistics. It has dexterous arms for grabbing things, but it sits on a stable weed platform, and critically, it boasts an 8-hour runtime.
Way better than the 2 to 4 hours for current humanoids.
Exactly. It underscores that crucial trade-off, the potential long-term generality of the humanoid form versus the immediate specialized efficiency you can get with a different, perhaps simpler design for specific environments.
And then way out on the other end of the spectrum, there was news in soft robotics, too. Hydra spread.
Yeah, this came out of the University of Virginia. Totally different approach. Hydra spread isn't a robot. It's a new manufacturing technique. It allows researchers to create incredibly thin, complex polymer films directly on the surface of water.
Why is making them on water better than on a solid surface?
Traditionally, making ultra-thin films on solid substrates is tricky. They tend to tear or wrinkle when you try to peel them off. Using the water surface acts like a perfectly smooth, self-healing, gentle workbench. It allows for much finer detail and more complex shapes without damage.
And these shapes can become robots.
Tiny ones. They demonstrated little insect-like soft robots like the Hydra buckler and Hydra flexor. These things can actually paddle or walk on the surface tension of the water.
Wow. What would you use those for?
Think environmental monitoring in lakes or oceans, maybe delicate inspection tasks, things where conventional, heavy, rigid robots just can't go. It's a great reminder that the future of robotics isn't just about humanoids and factories. It's incredibly diverse.
Okay, so we've seen mind-blowing progress in AI, simulation, physical agility.
Yeah.
But let's be realistic. What are the big roadblocks that still remain? The sources we looked at were pretty clear that some fundamental hardware challenges haven't gone away.
No, they haven't. And these persistent limitations are probably the biggest drag on mass deployment right now. The number one bottleneck: energy, power, batteries.
Still batteries.
Cell batteries. Our research team confirmed across multiple sources. Current humanoid prototypes. You're typically looking at only 2 to 4 hours of operational runtime before they need to plug in, often for a long recharge.
2 to 4 hours. That's
Yeah.
not even half a standard work shift.
Exactly. Compare that to specialized autonomous mobile robots, AMRs, the wheeled kind used in warehouses. They often run 10, 15, even 20 hours, sometimes with hot swappable batteries for near continuous operation. If your expensive humanoid can only work for a quarter of the day, the economic justification gets really, really tough in the many industries.
And why is the battery life so short? Just the power needed for walking.
It's the power density needed to drive all those high-torque motors in a human-sized form factor doing dynamic tasks. It's an enormous engineering challenge to pack enough energy into a reasonable weight and volume.
Okay, energy is bottleneck one. What's number two?
Dexterity. The hands. While the AI brain, like Gemini, can reason about how to fold origami or handle a delicate object.
The physical hand might not be up to the task.
Precisely. Robotics experts consistently point this out. Replicating the sheer nuance of the human hand, the fine motor control, the rich tactile sensing, the ability to apply just the right amount of force almost subconsciously is incredibly difficult.
We take our hands for granted, but they're marvels of engineering.
Hundreds of sensors, complex actuation, trying to build that reliably, durably, and cost-effectively into a robot hand. That remains maybe the single biggest unsolved hardware problem in humanoid robotics. The robot might understand fragility, but its current fingers might still crush the egg.
So batteries and hands are the main hardware brakes holding things back right now.
Yeah.
Looking further out, though, was there anything suggesting a future accelerator? Something that could maybe overcome some of these limitations, especially on the AI training side.
There was one particularly intriguing piece of academic research flagged by the team. A proof-of-concept paper exploring something called quantum deep reinforcement learning, QDRL.
QDRL. Okay, now we're definitely in the future. Quantum computing for robot training. Why is that potentially such a big deal?
Because training these advanced robots, especially for complex skills like walking robustly on uneven ground using classical reinforcement learning, it takes an astronomical amount of computation, millions, maybe billions of simulated trial and error steps.
Which costs a fortune in computing time and energy and slows down development massively.
Exactly. It's a huge bottleneck for creating truly general, adaptable AI. This QDRL paper explored using quantum computation to speed up a critical part of that learning process.
How does the quantum part help?
They used a hybrid approach. Classical computers managed the overall system, but a quantum processor was used specifically for the policy optimization step, basically. The core search process, where the algorithm figures out the best sequence of actions, the policy, for the robot to achieve its goal.
So the quantum computer is better at searching through all the possible ways the robot could move.
That's the idea. Classical computers can get bogged down exponentially as the problem gets more complex, more joints, more environmental variables. Quantum algorithms, at least in theory, can explore these massive high-dimensional search spaces much more efficiently for certain types of problems.
And did it work? What was the efficiency gain they reported for training a complex humanoid task?
The results were pretty dramatic, at least in this initial study. The QDRL enhanced algorithm learned a stable walking gait that was competitive with the purely classical approach, but it required 92% fewer training steps to get there.
92% fewer steps. That's not an incremental improvement. That's a potential phase shift.
It really is. If you can slash the training cost and time by that much, suddenly developing much more complex, much more capable AI models for these robots might become economically and temporally feasible.
It changes the whole long-term outlook. What seemed maybe decades away in terms of training complexity could potentially be compressed into just a few years.
Exactly. QDRL or something like it could be a powerful future accelerator. It doesn't fix the battery or hand problems directly, but it could drastically speed up the development of the AI brains needed to make the most of whatever hardware we have.
Okay, so let's try to synthesize everything. We've covered AI reasoning, platforms, physical agility, deployment strategies, bottlenecks, even quantum accelerators. What are the big takeaways from this truly pivotal week in late September 2025?
I think there are three main conclusions that emerge from the consensus view. First, the AI side, the reasoning, the VLAs, the planning. It feels like it's currently advancing faster than the core hardware capabilities, especially energy and dexterity. The brain is outpacing the body, in a sense.
Yes, that may take away.
The fundamental bottleneck seems to have shifted. For years, the question was, can we even build a robot that walks reliably like a human? Now the answer is increasingly yes. The main question is shifting to, can we make them smart enough, reliable enough, and energy efficient enough to actually operate autonomously and usefully in complex human environments for extended periods?
So from mechanical possibility to intelligent practicality.
Exactly. And the third point is the acceleration driven by standardization and democratization. Open platforms like Nvidia's Isaac, new ideas like Skill's Omni-Bodied learning, they're lowering barriers, speeding up development cycles, and pushing the whole field towards real-world deployment much faster than many expected.
So looking ahead then, based on these trends, what should we realistically expect to see in, say, the next 12 to 24 months?
Based on our analysis, probably three key things. First, expect a significant ramp-up in pilot programs, especially in structured environments like logistics and manufacturing, as companies leverage these new platforms and capabilities.
More Apollos in factories.
Probably. Second, I think we'll see more experimentation with hybrid locomotion designs. Maybe robots that combine the efficiency of wheels for flat surfaces with the versatility of legs for obstacles or stairs, trying to get the best of both worlds.
Makes sense. And third,
Increasing calls for, and maybe the development of, standardized autonomy audits. More rigorous, independent verification of what these robots can actually do autonomously, separate from the marketing hype. The Pop-Timus question isn't going away.
fascinating. It feels like we've crossed a threshold. We're rapidly figuring out how to teach robots to reason like us and move like us. The convergence of smarter AI and standard platforms is making it happen. But it leads to maybe the biggest question of all.
Which isn't technical at all.
Right. The technology is accelerating incredibly fast, but the ultimate challenge might be societal. How quickly can we, as humans, adapt and prepare for the arrival of these increasingly capable thinking machines into our daily lives? Are we ready for the robots that are undeniably rising?
That's the multi-trillion-dollar question, isn't it? The robots are learning our world. Now we need to figure out how we want to live with them.
A lot to think about. We definitely want to hear your thoughts on this. Whether you're watching on YouTube or listening on your favorite podcast app, please drop a comment. Let us know what you think about this rise of the thinking robot. Thank you so much for joining us for this deep dive on Tomorrow Unveiled.